So let's consider a rod that has a certain length, and it's just sitting in front of us, and we measure its length. Say the pencil, right? So the pencil has some length, and we can measure its length with a meter stick. And on the space-time diagram, that pencil, let's say if the eraser end is at what we call the origin, and this tip here is at some distance there, then that's the pencil on the space-time diagram at t equals 0. That's t and x, and of course we're just going up along the space-time diagram, right? So this represents putting the pencil down at t equals 0 and leaving it there for all future times, right? So the front end just moves up and the left end just moves up on the space-time diagram. From the perspective of a moving observer, t bar, x bar, right, we can ask the question, what is the length of that object? And the length of that object is actually something along this line, right? Because that's the spatial axis. But let's just, right, so let's say the length of the pencil is L naught. From our perspective, where the pencil is just sitting there in front of us. And we want to find a way of measuring, figuring out what the moving observer measures for that object. So one way of doing this is to imagine, think about the moving observer. So this is the path on the space-time diagram of the moving observer. So the moving observer is moving towards the right end. And therefore, from the perspective of the moving observer, the pencil, right, the moving observer can consider himself or herself to be at rest, and so the pencil is moving to the left. And so the right end of the pencil is moving towards that observer at the relative speed of that observer, right? So the observer is moving with some speed v with respect to the xt observer. That's the relative speed. So the pencil, from the perspective of that observer, it's the right end of the pencil that's moving toward that observer at speed v. And so the length L of the pencil, or the rod more generally, is given by, right, the right end will reach that observer. It's moving toward that observer at a speed v, and it'll reach that observer after some time delta t bar, as measured by the clock on the moving observer's clock, who measures delta t bar. But we can think of this from a different perspective. So the observer that's at rest can measure the length of the pencil in the same way by clocking the time it takes for the moving observer to reach the right end, right? From the perspective of the observer where the pencil is stationary, then it's the moving observer that's moving towards the right end of the pencil, and that moving observer is moving at speed v. So L naught, which we imagine measuring at the beginning by just using a meter stick, we can now measure by thinking of the distance traveled by the moving observer and the time it takes to reach, right, the right end of the pencil. So the speed is the same, but the time is different, right, because now we're using a time on the clock that is stationary with respect to the pencil. And so we call it tau, or delta tau, right, sort of the rest clock. And these two are different. But we know the relationship between these two times, right? We already derived this. We know that delta t is dilated with respect to delta tau by this factor, 1 over the square root of 1 minus v squared. So time is dilated, so there are fewer ticks are recorded, and therefore it follows that L has to be less than L naught, right? Because we have fewer ticks, delta t bar, because delta t bar is dilated with respect to delta tau. And the factor is just this quantity. So it must be true that the length measured by the moving observer, the length of the pencil as seen from the perspective of an observer with respect to which the pencil is moving at speed v, has length 1 minus v squared square root L naught. And that's length contraction. Right, not really a surprising result in that time dilation and length contraction are just there, are what follows from the fact that the speed of light has to be the same for all observers. Right, so in a sense, both space and time have to be less such that the speed of light remains constant.